All right, so they're independent. His shirts, so the shirt he puts on and the pants he puts on, they have nothing to do with each other. They're totally independent. So, all right, well, let's see. I'm going to multiply two numbers together. The first number is how many it is from the first set. Well, shirts are the first set. So we know he's got 3 shirts. We know he's got 2 pairs of pants, and they are totally independent. So if I take 3 times 2, I get 6 events. 6 events can possibly occur. And it makes sense. He could have yellow gray pants, yellow blue jeans. He could have blue shirt, gray pants. He could have blue shirt, blue jeans. A little tacky, but he could have that. Okay, and then he could have red shirt, gray pants, red shirt, blue jeans, which is a total of 6 combinations. Now, I don't want to have to keep counting like I just did there to show you that this 6 numbers is valid. I just want to use this formula in the future because sometimes what we count gets very large. And finding all possible combinations gets very difficult. It's just easier to use the formula. All right, on to our next problem. And pants. So let's see, how many shirts does he have? He's got 4 shirts. How many pants? He's got 3 pants. So it turns out he's got a total of 12 different possibilities. So he almost has 2 full weeks of different clothes he could wear without ever quite exactly matching the same combination.
0. So the product of an integer and all of the numbers below it or less than. Okay, so let me give you an example and let me show you what a factorial actually looks like. So if you have 7 factorial, this exclamation point is the factorial. That is equal to 7. That's the integer that I have, times 6, times 5, times 4, times 3, times 2, times 1. And 7 factorial is equal to 5,040. So I just multiplied 7 times 6 times 5 times 4 times 3 times 2 times 1. If you are on Desmos and you would like to find the factorial of a number, all you have to do is you go to Desmos.com, you type in the number that you want to find the factorial of. So for example, 3. If you type 3 and then you physically type the exclamation point, it will tell you what that's equal to. This one's kind of easy because you just do 3 times 2 times 1, which is 6. If I have socks in a drawer, right, and there's 3 different colors. So let's say I have 5 blue socks, 2 red socks, and 4 yellow socks. Okay, so the probability of blue on my very first sock is there's 5 total blue socks out of 7, 11 socks. And then the probability of red, that's going to change if I don't put the sock back. So the probability is 5 out of 11. The probability that the next one is red is going to be something out of 10. Now, if my first sock that I picked was red, then it would be 1 out of 10. If the first sock that I picked wasn't red, it would be 2 out of 10. So you see that the probability originally changed depending on what happened in my first one. So it's a dependent event if the probability of the second event is affected by what happens in your first event.
We add the fractions together and subtract the overlap. I know right now you're like, what? We'll get to that. Uses the word and. You're going to multiply the fractions together. So this is on page 26. The card is randomly selected from a standard deck of 52. There's 52 total. There's 4 different suits. That's your spades, hearts, clubs, and diamonds. Okay, so what is the probability that your card is a heart card or a face card? Okay, so hearts are all of these, the ones with the hearts on them. So if there's 52 total cards and there's 4 different suits, that means each suit, that's what we call these, the different symbols. Each suit is 13. There's 13 of each. And you could count on that, like count them and see there's 13, or think about it as 52 divided by 4, because there's 4 different suits. Okay? So picking a heart, there's 13 chances to pick a heart out of the 52 total cards. Okay? And then it says, or a face card. A face card is one that has someone's face on it. So those are Jack, Queen, and King. Let's see. So these are all your face cards, right? Jack's got a face on it. Queen's got a face on it. King. So how many are there? This is 1, 2, 3 times 4. There's 12 face cards. So 12 face cards out of the 52. But here's the problem. It's that reminder that you have to subtract the overlap because we don't want to double count cards. So there's 13 hearts and there's 12 face cards, but you've got to ask yourself, are there any that are both heart and face cards? So that's when I look at this study sheet again. Here's all my hearts. Oh, look, there's 3 of them, right? We got the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So that's what they mean by an overlap. They're face cards and the hearts. So we've got to subtract those, otherwise that probability, we're adding 3 more chances that are not there because they're the same thing. So you're going to subtract the 3 that are hearts and face cards. So I purposely picked a pretty tricky problem. So 13 plus 12 is 25 minus 3. So your probability of choosing a heart or a face card is 22 out of 52. And you could put this into Desmos to see what that probability is. I think this one's a lot harder than what you're being asked to do for homework, but I figured I would show you an example of that one. So you got a 42.3% chance of picking a heart or a face card. So these are your and ones. So this is the one where we just talked about a second ago. The and ones, you multiply your fractions together. Let's see. So you flip a coin and you land on heads. So to flip a coin and get a head, you've got 1 out of 2 chances, right? 50-50. That's what we say a lot with flipping coins. Getting heads or tails, 1 out of 2. And means you're going to multiply. So rolling a 4, you have a 1 in 6 chance, right? There's only 1 4 on a dice. And since it says and, you're multiplying. Multiplying fractions, 1 times 1 is 1. 2 times 6 is 12. So you have a 1 out of 12 chance that if you flip a coin and then roll a dice, that you'll get heads when you flip the coin and a 4. So both things have to happen. So a bag contains 5 blue marbles, 6 purple marbles, and 9 red marbles. Okay. So if you want, before you even start, you could figure out your total, which is 5 plus 6 is 11 plus 9 is 20. So there's 20 total marbles in a bag in my hand. Okay. What is the probability of getting a blue marble and then a red marble if you replace the first marble before choosing the second? Okay. So I know that's a lot, one thing at a time, right? So probability of getting a blue marble. Okay. Well, there's 5 blue marbles out of 20, right? That's this right here. And then the and part is the reminder that we have to multiply, because the first one depends on the second one. No, actually, they don't depend because I'm replacing it, but the and then is saying this is really specific. I need this, then this in that order. Okay, it's not saying and blue or red, either's fine. It's saying, no, I want you to pick a blue and then a red in that order. So that the multiplication makes it a lot tougher. Your final result's a lot tougher to figure out. So 5 out of 20 is the chance for a blue marble. Remember, I take out that blue marble and it says you replace this bold part. You replace the first marble before choosing the second. So put that blue marble back. So our total is back to 20. You got 20 marbles. So now selecting a blue marble, sorry, a red marble, keep switching my colors. Blue marble's 5 out of 20. Red marble, we've got 9 out of 20 options. And since it said and then, you multiply them. So multiplying across, you get 9 times 5 is 45. 20 times 20 is 400. It reduces to